this one. So let's write this first one down somewhere. It's not exercise. Just understand this one. So what is the order of operation of this one? What is the first thing you do? Differentiate. You differentiate first and then integrate later, right? Then they annihilate each other, right? Differentiate again and integrate. Integrate means going backwards. Only thing is that when you integrate, you have to throw in this constant, right? That's all derivative. Sometimes, rather than just talking about this, all the antiderivative, talking about specific antiderivative sometimes better when you're solving equation. For that one, you don't put indefinite integral symbol, but you actually put definite integral symbol, but keeping this upper limit as a variable. Then it pinpoints a very specific antiderivative. Okay? So not just anything in here, we're talking about very specific capital C here. So what is the antiderivative inside function? Little f of t. That is an antiderivative. So if you evaluate x and c, you get this one here, right? So that's an antiderivative, but very specific antiderivative. So sometimes it's better to deal with this one like this. Does that make sense? So you understand this procedure, differentiate and integrate, but this is how it's written. And if you get used to it, you think much more efficiently sometimes. How about this one? Integrate first and differentiate later, right? Then obviously it's f of x, right? Hope that makes sense. And then this is again very specific antiderivative, right? Of f of t. Then if you differentiate it, of course you go back to the original function, right? But this is how it's being written, and you better get used to this. All right. Question about this one? All right. By definition of antiderivative, that's pretty clear. So here's our first problem. First one here is homogeneous, right? Left-hand side and right-hand side is 0. It's a linear, it's a homogeneous linear equation of first order. And a is a constant. So if it's easier for you to think about it, that a can be -1 or 2, that kind of constant, all right? Rather than px, a function. It's a constant. So we want to solve this equation first. So I sketch the direction field when a equals -1, then it's going to y prime plus 1 plus y equals 0, right? And that's the equation. Do you see easy solution? Yeah, the 0, because it was homogeneous solution, you always has this trivial solution. It's right there. Okay? This is direction field, and this is actually a collection of solutions called integral curve in the book. So let me show you how to solve that one. First approach is just purely calculus approach. Y prime minus ay, a is a constant, equal to 0. I'm going to manipulate this one. What we learn in calculus 1 and 2 is just integrating, right? So we're going to integrate by isolating it like this, ay. Fair enough? And they collect these y's together like that. Like this, and it equals a constant, right? And you can do that when the function does not hit 0. So here's something that you have to be careful about if y equals non-zero, right? So we're looking at small neighborhood such that function does not hit 0, then you can put that in the denominator, right? So then what you can do is that if you put now the integral operator in there, and you can integrate it. So I'm going to put it here like this, y prime, y and dx is our main variable, and here a and dx. Right-hand side is easy to integrate, right? Right-hand side is easy, so I'm going to put it like this. Ax plus c. Is that okay? Capital C with that hook there. If you have to integrate like this, not knowing what y is, but if it is in this shape, there are integration techniques, right? What are the integration techniques? You have substitution, integration by parts. There's a trigonometric substitution. That's pretty much it, right? Okay? So which method do you think it works? By parts could be done. U substitution works, right? So what is a u? U is y, right? So what is du dy? with du dx is y prime. So and this one becomes y prime. U there, and is reciprocal. It's y prime there, and switch to du. However you do it. Does that make sense? The reciprocal goes in there. So this y prime cancels, and you're left with 1 over u. Du is equal to a times x plus c. So we treat this little a as a known constant. And let's see if you can integrate left-hand side. ln absolute value of u, not just u, right? Absolute value of u plus c, but since we have already seen there, is it okay if I just proceed like this? Ax plus capital C. Good? Now you want to isolate this for y, right? So it's going to be like this. For u, absolute value of u, which is really y. So I'm going to put y in there. So it's like this. What is the absolute value of y? Yeah, how can you change from logarithm form to exponential form? E to the, right? E to the ax plus capital C. But exponential law, you can separate this nicely like this, knowing this is a constant, right? E to the c not only is a constant, it's a positive constant, don't you think? So you know this is a constant, and it's a positive constant. Okay? So when you really solve this thing for y, without that absolute value, and there's going to be e to the ax times e to the c. I'm going to call this part, that may be plus and minus, right? I'm going to call that one delta x, where delta x assumes plus 1 for some value of x, minus 1 for some value of x, we don't know. But if you sketch these functions, and if this really switches to positive and negative as we vary x, you can easily see that it loses the continuity. Sometimes there's a positive here, plus 1 over there. Sometimes it's negative. In the next, right next to x value, become negative there. You lose this, continuity. You can't go back and forth plus minus like that, right in the neighborhood. So this is actually always 1. Is this 3 bar make sense? It's always 1 or always negative 1. Because we expect y is, at the beginning, we started with this type of equation that is even differentiable, right? Differentiable means it's continuous. So we expect solution of this thing to be continuous solution if it flip-flop, and it cannot be continuous. So either is a positive 1 or negative 1 all the time. If it is a positive 1, and it's going to be just like that, if it is a negative 1, this positive constant becomes a negative constant. So altogether, out of all this observation, you can write y equals some little c and e to the ax, where c is arbitrary constant. It can be negative or positive because it's positive, negative. With a positive constant, it covers everything. Okay? So we found a solution. Any constant, it could be 0. If c is 0 and y equals 0, you know is a trivial solution, right? It is a solution. And if it's anything else, this will satisfy the differential equation. And then you can actually, just verify that you plug this one into original differential equation, and you can verify that. We have practiced that, right? But there is this issue of y not equal to 0, and then you have to take care of it, things like that. So after you discover the solution looks like this, and I'll introduce a slightly better idea, that argument is a lot cleaner than this. And we'll stick to that to actually prove this is the older solutions, and there is. Okay. So A is fixed, that giving you one equation, and C gives you many solutions to the one equation. But we switch the little c to cover all of them. Does that make sense? All right. So I'm going to give you a slightly different way of checking this one. The equation was y prime minus ay equals 0, right? And we want to see that y equals c times e to the ax is actually the solution of that. Okay? I'm going to verify that you can differentiate and all that. But here's a fun way of doing it. I'm going to isolate c, then is y equals y times e to the negative ax. Is that right? If you multiply reciprocal, and that's the same thing as negative exponent. Fair enough? I multiply e to the negative ax both sides, and then arrive at here. In that process, I don't have to worry about denominator being 0. This is actually dividing it, right? Because the exponential function never hits 0. Therefore, when you divide it, you don't have to consider denominator being 0 or anything like that. So that's very clean. Next thing we can do is differentiating both sides. So I'm going to write it like this clearly. Y times e to the negative ax equals d dx of c. Fair enough? So what is the left-hand side? Somebody try this one. Right. Let me differentiate the first one first. There's y prime there, right? E to the negative ax. Correct? Differentiate the second one. What do you get? Negative a is multiplying negative e to the ax. Is that right? Is equal to 0, right? What's interesting about e to the exponential, when you differentiate it, it's always there, right? And you know it's non-zero. Non-zero. And then we can cancel that, right? Then what happened? Y prime minus ay equals 0. So we didn't really plug in e to the negative ax, but you can manipulate our discovery like this so it actually satisfies. Right? So this is one-way implication. If y is this particular function, then this follows, that follows, therefore this follows, right? What's fun about this process is that can we reverse it? If I started with like this, I don't know what y is. I don't know what y is, but it satisfied this one. But let's reverse it. If it is this function, is this true? Going backward, this was true, right? I can just multiply known equation by anything, and this is true. If this is true, without knowing what y is, this must follow, right? How about here to here is the most difficult part. If you see this left-hand side expression, you don't immediately recognize it's a result of a product rule. But we've seen it already, so the logic is correct. This one is a result of a product rule of this particular product. Don't tell, you don't have to ask how I discovered it. It just came to me last night, and it is true. And then you can just give it as a proof. Oh, I discovered it. Don't ask how I discovered it, but it is true. So because of that fact, that left-hand side is true, right? Yeah. Proof does not require how you discovered it. It's just if it is correct, it's a proof. So you go back there. Then you can integrate both sides with a 0 here. Instead of c, you have a 0 in there, right? But if you integrate 0, what is it? Constant c, right? And then if you integrate that, of course, it becomes this. And therefore, you arrive at here. So if you start with this function in here, not knowing what y is, and this backward argument shows that it has to be this guy. Right? So if you think about the existence of a solution or uniqueness of a solution, this backward argument, which one do you think it proves? Existence of a solution or uniqueness of a solution if you argue it backwards? The uniqueness. If you start from here, you don't know whether the solution exists or not. But if it exists, then it has to be this one. And that's the uniqueness proof. Let me say it again. We start from this argument here, right? You set equal to 0. At that point, we don't know if it has a solution or not. But the argument is that if it has a solution, then it must be this one. Therefore, it proves uniqueness. There's only one function like this. Because of the C, I call it semi-uniqueness. If you change C, many solutions, but it's all in that form. And in the textbook, you often see that then they do this, and then they plug it in here and verify that is actually the solution to that equation. And you feel like that is really unnecessary. Didn't they just solve that equation? And why are they checking this one again? It's because this argument does not prove that this is a solution. It only proves if there is a solution and that's the only one. And then it requires an argument, is that really a solution? Then they have to check the solution to make the argument solid. right? Can you imagine a situation like that? X to the square plus 1 does not have real solutions, right? Everybody knows that. Suppose it's in complicated form. You didn't know this, actually this solution, and you manipulate it by squaring both sides like this, and you end up at here and be able to find the solution plus minus 1, right? You do this manipulation and you arrive at here, x plus minus 1 works, right? But you know that's not the solution to that equation. It is exactly this argument. If you started with a false assumption, suppose there is a solution, and you manipulate it like this and arrive at here, if there is a solution, it must be either 1 or minus 1. But none of them is actual solution, right? Therefore, your assumption, if there is a solution, is false. There isn't any solution. Therefore, it's sometimes worth checking this thing that you got at the end is actually a solution or not, right? But if you understand the both-way reversibility of the argument, it's natural. So sometimes people don't check because they understand, but sometimes they check it for the audience and the reader. Right? These are called existence and uniqueness. And if you one's having trouble with understanding the logics behind all this thing, I hope this example helps you. All right? So let me resolve that problem one more time again. If I have something like this equation, e to the y prime of x, y equal to 0, then there was a product rule involved in all this, right? Remember when I was reversing, there was a product rule involved, and there was e to the something involved in there too, right? But you don't see it here, and it's very difficult. If you're staring at this one like 10 hours, you still might not be able to come up with this multiplying e to the something in there, so all the magic works, right? But we've seen it before from different technique, right? Earlier, doing the y prime divided by y, we discovered the solution by studying how the solution works. We discovered this technique of multiplying exponential function in here. Okay, so I'm going to give you that factor. That was a before. A in front of it here, right? What did we multiply it in here to the left-hand side and right-hand side when you go backward? E to the ax, the relationship between a and ax, is the antiderivative. So the correct technique in here, we're going to multiply both sides by e to the something, x times e to the something there, and y equals 0, which is allowed, right? Such that its antiderivative in here, x, appears in the exponent part. So what is the antiderivative of x? 1/2 x squared, right? But there are many antiderivative, but you can choose this one, and that still works. So I'm going to put it like this. And here, antiderivative of x is 1/2 x squared. Is that right? Now, once you multiply this right fact, you can see that this is a product of something. If you don't see this is a product of something, then you can do integration by part. Remember, integration by part is a reverse of a product rule, right? So here's a two passages here. If you see this is a product of derivative of a product of something already, great. You can just write that down. Do you see what that is? Y is there, right? You can put it in there. Right, e to the 1/2 x squared is the answer. If you differentiate this one, you get y prime, right? And this one is not differentiated. If you differentiate that one, y is untouched. When you differentiate this one, e is there. Derivative of exponent is x, right? Therefore, x appeared there. You verify the derivative of this one here is precisely left-hand side. So you can do the reverse. If this is really uncomfortable, don't know what to do, then they prepared, they have this technique of integration by part for you. So which is what I'm going to do next. So integration by part is not necessary. If you see this directly, that's great, do it. But let's put the integration in here, just in case you don't see this. Y prime dx equals x times e to the 1/2 x squared, y dx. What happened if you integrate right-hand side? C. Is that good? All right. Which one do you think you have to apply the integration by part? You have to only do the one part. We're going to do the first term or second term. If you do the integration by part in here, and you can integrate this part easily, right? From that, you can get rid of y prime. Good? So can I make that one exercise? Exercise number 2. Compute this integral using integration by part. So how about integration by part, apply integration by part to this guy. That's exercise. I hope this is clear enough. You see product of two functions, right? You integrate one factor and differentiate another one. That's integration by parts. Right, if you apply integration by part one times and you get rid of y prime and becomes integrated, so it's just y. And if you differentiate it inside integral, it looks like this. If you differentiate this e to the 1/2 x squared, you have x times e to the 1/2 x squared, right? By chain rule. Make sense? That's the result of applying integration by part to that part. So you see that if you replace this one with this thing, and you see this and that cancel with the plus and minus, right? Leaving only that part. And that's the left-hand side. So that one in here now, with this exercise result, left-hand side is this one and that, and these two cancel, and leaving just this one. And right-hand side is C. Right? Yeah. Which I got this one by just looking at this one as well. If you recognize this is, derivative of this product, then you can just write it like this. I didn't integrate it. I just wrote this left-hand side as a derivative of something. And right-hand side is 0. Now if you integrate this one, then you will arrive here directly. So let me proceed here. Put the integral symbol. We practiced this one before. Right-hand side, if you put integral symbol, that's a C here, right? But what is left-hand side now then? Differentiate and integrate. They cancel the same thing as an inside there. It's e to the negative 1/2 x squared equals C. I missed y there, so y should be there. And y is there. Equal to C. Now you solve for C here at this state. Now we have the same form there. Y equals C times e to the negative 1/2 x squared, right? So this whole argument shows a uniqueness or existence. Uniqueness, right? We start with suppose there is a solution that satisfies this one, and all this argument says it must be this guy, right? But is this really a solution? Then you have to plug back in here and check if it is really a solution, right? That's the existence. Okay? Make sense? All right. So I'm going to save that. Now you have a general solution for this type of problem. If they give you an initial value problem, you can compute that C, right? By plugging in that data. So this part B is easy. Okay, by plugging in this x equals x0, y equals y0 to that general solution to pin down what that C must be. Does that make sense? Yeah. So that's how you solve the initial value problem. And I already talked about all this. So I'm going to show you this problem in here. And for this problem, I'm telling you that you don't need that exponential factor. This one in here, integration by parts will work immediately. Before that example, we have to multiply this magic factor of 2 to the e to the something, right? Then it becomes magically the product of two functions. I'm claiming that this one is already in derivative of product. So either you realize that, oh, the derivative left-hand side, antiderivative left-hand side is this, or if that's not easy to you, then you can do the integration by part, just like we did, right? So that's our exercise number 3. Solve part A. What method are we using? Integration by parts. That's what we're doing. Put the integral symbol. It's linear, so you separate it over this addition. You work on the y prime part. Apply integration by part to x times y prime. Right, how's part A? Does that make sense? Yeah, if you integration by part, the first part, if you integrate y, you're left with x times y, and you differentiate x, inside there's 1 times y. So result of integration by part to the first term is xy minus integral of y. But out there, there's a plus integral of y, so they cancel, giving you non-integral expression. There's no derivative, no integral, just x times y equals c. So y equals c over x. You know how the c over x looks like, right? For example, c is 1. Do you think that picture coincides with what you see in the direction field over there? Like functions like this. Hyperbola. That's like y equals 1 over x, right? And if c is negative number, it'll be over here, stuff like that. Make sense? Yeah. Let's solve this one together. If you're looking at this one, homogeneous equation, that's the general equation, right? When x equals 1, y equals 3, that one in there, and in part B, x equals 1 and y equals 3. So if you plug it in there, it's a 3 equals to c over 1. So what is c? 3. For that one, we have a solution being 3 divided by x. That's uniqueness, right? So the solution to this homogeneous equation with this initial value, and there's only one solution. This is really called uniqueness, and the uniqueness I was talking about here is kind of semi-uniqueness. We can pin down to a very uniform shape like this one, and I call it semi-uniqueness. And this is usually what they call uniqueness. Actual function, there's no C in it, which is caused by this additional condition and put it in there. All right. One last thing I'd like to mention in here. In general, if you see this equation, homogeneous equation like this, right? One that we just did here, you don't have to multiply anything, right? But the magic is that you multiply this capital P, both sides, like this. Then magic happens to left-hand side. Left-hand side, if you do the integration by part, or we try to realize it as a derivative of product rule, it works. What is this capital P? Antiderivative, right? Differentiated, you get that little p out there. So if you're staring at this function, you can think about, oh, antiderivative, put it up there in exponential form, and multiply both sides, and then magic happens. Yeah. Who would have thought by looking at that equation? But it came from the original approach. If that e to the something is involved, then this is a clearer argument, although it doesn't share. How did you discover that, right? The very first approach shows you how it was discovered. Once you know it works, and this is the method we use. All right? Okay.